My name's Harry. This is a joint work between myself, Gabrielle Beck, Matthew Green, Nadia Heninger, and Abhishek Jain. So let's talk about the offline finding ecosystem. Specifically, let's talk about location tracking accessories. So what are these? These are lightweight devices that you can use to track your objects. The most famous of which is the AirTag. So I might say AirTag or tag throughout this talk. LTA is the umbrella term because a number of companies make these. They work via this crowdsourced location tracking system, and you get a nice map on your phone that shows you the location of your object. So how does this work at an extremely high and somewhat incorrect level that will suffice for this talk? Your AirTag, when it detects that it's lost, will start broadcasting an ID. It'll say, hey, this is my ID, help me get found. This is my ID, help me get found. This is my ID, please help me get found. And so what are some risks of having a system like this? Well, one is tracking. So in this, an adversary that has a sequence of Bluetooth receivers, the AirTag is broadcasting over Bluetooth, can actually track your location via your own AirTag. And it does this by, you have these Bluetooth receivers at locations of interest, and then it may see the same ID broadcast in 3 different places. From that, it can assume that this is the same tag, and it's now tracked your location. Okay, so this is very bad, but what is a potential solution to this? Well, maybe you just rotate this ID more often. Unfortunately, that runs into trouble with one of the second major difficulties of these, which is stalking, right? If I'm a stalker, I can place one of these LTAs inside my target's backpack, or I can tape it underneath their car or something like that, and suddenly I can now track their movements. This is also very bad, and these major companies have a built-in mitigations for this, in which your phone will alert you if it thinks you're being stalked by an AirTag or some other device. It'll say, hey, I think this has been with you for a while, and you can go make a noise now and go find it and remove it. So how does this happen? Well, it looks for the same ID in multiple locations, right? If it sees the same ID in 3 different places over the course of some time, it might say, hey, I think you're being stalked by this tag, so this is now a danger to you. Okay, so these are both bad, and what sort of mitigations are built into the system right now? Well, right now, we make a sort of pretty serious compromise, which is that the ID the AirTag is broadcasting rotates every 24 hours. At least this is how it works for Apple's scheme. This means that you can detect stalkers very well, right? Because they'll be broadcasting this constant ID, but it means that honest users can be tracked by these tracking adversaries for a full day, right? And so this is not very good. And the question we ask and hopefully answer in this paper is, can we do better? So you might be wondering, why can we even do better, right? Where's the hope here? The goal of a stalking victim and the goal of a tracking adversary seem really similar. They both want to detect if they've seen the same AirTag a number of times. Well, here's why there's hope. So a stalking victim is going to be in continuous proximity to the LTA, right? They're being stalked by it. They're going to see pretty much every broadcast it emits, whereas a tracking adversary will only see these broadcasts in short bursts, right? It only sees broadcasts from my AirTag when I happen to bike past one of their Bluetooth receivers. So what we want is a scheme where you can only link these broadcasts together. We know that they're from the same tag if you've seen enough of them, right? We have some sort of threshold thing that we want. Okay. So so if we're doing thresholding, a very natural place to start building something like this is with secret sharing, right? So what is secret sharing? You have a secret, it's owned by a dealer, splits the secret up into shares. And then if you have enough shares up to some threshold, you can pass them to a reconstruction algorithm and get the secret back out. The corresponding security property is if you have under the threshold number of shares, you have no idea what the secret is. So maybe we can use this to build a scheme, right? Maybe instead of broadcasting an ID, AirTags broadcast a share of their ID, right? And now we can be unlinkable because the shares look very different from each other, right? They're just sort of points on a polynomial if we're using Shamir sharing. And I can reconstruct the shares in order to tell if I'm being stalked or not. If I can get something back out, then I'm being stalked. Unfortunately, this doesn't quite work for this example. It's not appearing on my screen, but it is there. Great, okay, sorry. So say I'm being stalked by 2 AirTags, and there's one honest AirTag that I happen to pass. The 2 that I'm stalking, I'll see a bunch of broadcasts from them, and I'll see only a couple broadcasts from the 3rd one. And now I just need to reconstruct these shares to get the secret back and tell them I'm being stalked. Unfortunately, I have no idea which shares correspond to which tag, right? So this clearly can't work because you need to only pass in shares that come from the same dealer to the reconstruction algorithm in typical secret sharing. We could put some sort of identifier on every share, right? Now we know which ones to construct, but this can't work because now we're back at square one. A tracking adversary can just look at those identifiers to track people. Okay, so secret sharing alone isn't enough. So what we do in this work is we introduce a new primitive we call multi-dealer secret sharing in order to deal with this. So what is this? Well, it's secret sharing with multiple dealers. We now have 3 dealers. They each split their secret up into a number of shares. And now we can take any collection of these shares, toss them into the reconstruction algorithm. We don't need to know which dealer each share corresponds to, and we'll get get back the secrets for which there are sufficient numbers of shares in the input, right? In this case, 3. So here, pink and yellow are what we call sufficient dealers, right? Because they have a sufficient number of shares up to the threshold, whereas blue is an insufficient dealer. There's also a corresponding security property, which we call unlinkability, which says that if you up to some other threshold, if you have only that number of shares, you have no idea if they came from one dealer or multiple dealers. You can't deduce the relationship between the shares at all. They are, unlinkable. Okay, so how does this help? Well, let's go back to our previous example. Which again, my slide doesn't take a while to load. Okay, so we're back in the previous example. Now we can just take all of those shares, toss them straight into the reconstruction algorithm. We don't need to know which tags they correspond to, and we can get the secrets out. We now, because we recovered some secrets, we know we're being stalked, and my phone can send me an alert. Okay, so MDSS can help us here, but it can also help us against tracking adversaries because of that unlinkability property, right? Now, when I'm biking around Baltimore, and I pass 3 of these receivers, if my privacy threshold is 3, this tracking adversary has no idea whether these 3 broadcasts came from the same tag or from multiple tags, right? So it can now no longer actually track my location because it can't link them together. Okay, great, so MDSS can help us. Let's talk about building MDSS, but first let's talk about what makes a good MDSS, because this will determine a lot of valuable parameters when we actually implement this. So what makes a good MDSS? If I'm a MDSS dealer and I'm broadcasting shares, at some point, I'll stop being unlinkable, right? My anonymity is going to be compromised. So we call this point K. That's the variable we use. And then at a later point, I become detectable as a stalker, right? Even amongst other dealers and noise. So this is a higher threshold, which we call T. And then, maybe I keep broadcasting. And so what we would really like is if K and T were very close together, right? The idea is that we only want to compromise on my privacy or my, unlinkability when we detect me as a stalker, right? So that's one valuable thing with an MDSS is we want K and T to be very close. So there's another variable here, which we call D, which is the number of sufficient dealers that the scheme can tolerate. So in this case, if D equals 2, and I have a collection of shares where there are 2 sufficient dealers, everything works fine. But unfortunately, when you have a higher number of sufficient dealers, reconstruct starts to fail. Now, ideally, D would be unbounded, but the schemes we were able to build for this work, they force you to set what your maximum value of the number of dealers is up front. This corresponds to how many AirTags you can simultaneously be stalked by and still detect that you're being stalked. This is a compromise, but we think it's a reasonable one because AirTags, cost money, right? If we set D high enough and you're spending hundreds of dollars on AirTags in order to stalk somebody, you could have just bought a self-contained GPS receiver. You no longer need the cheap, $25 AirTag. Okay, so what we'd really like is we'd like D to be high, and we would like K and T to be close together. Those are what makes a good MDSS. Okay, so how do you build an MDSS? Let's think about it with one dealer. So that dealer has a secret, they split it up into shares, maybe there's some sort of noise in there from other tags. What's inside one of these shares? Well, in Shamir sharing, the dealer has chosen a polynomial, encoded their secret as the constant point of this polynomial, and then outputs a pair that's an x-coordinate, and then the polynomial evaluated on that x-coordinate. Sort of critical for unlinkability, all of these x-coordinates need to be sampled uniformly at random. Check out the full paper for more on that. But so now our goal as a reconstructor is we want to figure out what this polynomial is in the presence of errors, right? So you may notice this is the exact setting of Reed-Solomon codes. This is exactly what they do. So we can actually use that sort of off-the-shelf technology of Reed-Solomon decoders, get the secret back. Okay, great, but this is only D equals 1. What about D equals 3 or higher? So with multiple dealers, in this case, we now have multiple sufficient dealers. We want multiple secrets out. We can actually still use techniques from coding theory because originally we were doing unique decoding. This is essentially the setting of list decoding, where there are going to be multiple things you want to get out of the input if they have sufficient presence there. So we can just use a Reed-Solomon list decoder, get back the secrets, and we're good. So from one perspective, we're now done, right? We've built an MDSS, we've used this off-the-shelf technology, and it works. But unfortunately, the Reed-Solomon list decoders come with a downside, which is a bound they enforce between TK and D. And so all the equations I show here are going to be slightly wrong, but they're exemplary, and see the full paper for more on them. But essentially, what these enforce is that T is greater than K times D, which is not very good, right? As D goes up, this gap between T and K will also go up linearly in the number of dealers that we tolerate. So this is bad, and we would like to to get a better scheme, and to do that, we use a different kind of code. Specifically, we use this thing known as an interleaved Reed-Solomon code, where we pack a bunch more polynomials into every share. So a share now consists of an x-coordinate and then c different polynomials all evaluated on that x-coordinate, right? We've now packed a bunch more information into shares, so now maybe we can do better with our decoding. And in fact, we can. So there's a bunch of previous works that describe how to decode codes like this. Unfortunately, some of them were too inefficient, right? We want this decoder to run on smartphones, so it has to be fairly efficient. And some of them only didn't quite work for the error distribution we would have expected in our setting. You can see the full paper for more on that. And so we built upon this Cohn and Heninger 2011 paper to develop our own decoder for this that works for our error distribution. And we end up with a much more efficient one than some of the other works would have been, and with a much better bound. The downside is that we only have heuristic correctness. We haven't proved it's correct. Experimentally, it works, but that may make some of you uncomfortable. But very important to us is we now have a much better bound in which again, this is sort of approximate, where you have t is greater than 1 over c plus 1 times d plus ck. So what does this mean? This means the influence of d on that gap between t and k now goes much, it gets much smaller as you increase c, right? So we can get t and k much closer together, even when having large amounts of dealers. Okay, great. So we also went and implemented things, right? We want to make sure this stuff actually can run on these low energy devices, and to do so, we needed to make a bunch of choices about parameters when we chose our implementation. See the full paper for more on that, but here's a sense of what we did. We set d equal to 3. We said, okay, we want to be able to tolerate 3 simultaneous stalkers. We had these error tags cycle through their shares every 60 seconds, so a new share every 60 seconds. We wanted to detect a stalker in 1 hour, so this is essentially t expressed in terms of time, right? So we want to detect it within 1 hour. And doing this, we were able to stay unlinkable for 41 minutes, right? We consider this pretty good. That's like a 2/3 relationship between k and t, so we're very happy with this. But does it actually run on these low energy devices? Well, we implemented this on a puck.js, which is this little thing. It's the same system on a chip as an AirTag, and so it's about as close as you can get to AirTag hardware without hacking an AirTag. And it was able to generate these shares in under 1/10 of a second, so this works. And then we ran our decoder on a Raspberry Pi 3, which we consider fairly close to a sort of low-end smartphone, and it was able to decode while being stalked by 3 stalkers in a little over a second. So we consider that efficient enough. So in conclusion, we think that we've shown that balancing stalker detection and tracker privacy is possible in this setting, and we wish more people were thinking along these lines. Thank you.